All right, let's take a look at friction, one of our basic forces that we talked about when we did forces, and one that comes up quite often throughout physics. Friction is one of those forces produced in objects. It is a contact force that occurs when two surfaces rub together. It is often the bearer or the producer of the net force that's acting on objects. It opposes motion. It opposes motion when two surfaces rub together. Oppose means opposite of the direction that the object is traveling in. So if an object, like in my illustration here, is moving to the right, the friction that's being produced is off to the left. So when I say opposes motion, this is what I'm referring to. It is the opposite direction of the object's motion. It's caused by two surfaces rubbing together. All surfaces, no matter how smooth or rough they are in appearance, always have ridges and valleys. And these ridges and valleys will get caught up in each other as the objects slide over each other. And that's what produces the friction. There are two types of friction, static and kinetic. Static friction is the force that has to be overcome in order to get an object moving. So when it's stationary, it has static friction. Kinetic friction is the friction that you have to overcome in order to keep the object moving. Once it's moving, in order to keep it moving, you have to overcome kinetic friction, moving kinetic. Static friction is always greater than kinetic friction. This is why when people are trying to get really good fuel mileage out of their cars, they try not to stop very often. They'll start slowing down way before a red light in hopes that they never actually stop for the red light. The reason is, while they're rolling, it's kinetic friction that the engine of the car has to overcome. Once that car stops, then it's static friction that the engine has to overcome. Static friction is always greater than kinetic friction, so it takes more energy, it takes more fuel to overcome that static friction than does kinetic. So they try not to stop in order to save gas. Both types of friction are affected by two factors, the normal force and the coefficient of friction. Normal force was another one of those forces we talked about in the video on forces. If you have an object and that object is sitting on a surface, the force of gravity is going to pull down on it. We've learned in Newton's second law that we can call that force of gravity the weight of the object. Because it's sitting on a surface, that surface is going to push up on the object, opposite of the gravitational force. That upward push that counteracts the gravity is called the normal force. The normal force is equal to the weight of the object. So if the force of gravity or weight on this particular object was 10 newtons, that means the normal force is also 10 newtons. Normal force and weight will cancel each other out because they are opposite in direction and acting on the same object with the same magnitude. The coefficient of friction is the number that describes how those two surfaces interact. The lower the number, the less they interact. If you have a higher number like 1, which is an actually fairly large coefficient of friction, then there's a strong interaction between the two surfaces. The surfaces are rough, or there's some kind of intermolecular force there. There's something that's making the friction high. That's represented by the high coefficient of friction. If the coefficient of friction is very low, like 0.01, then that means the forces don't interact much at all. The ridges and valleys are very small. There's no extra intermolecular forces to interfere. There's not much interaction between the two surfaces when the coefficient of friction is low. Again, low means little interaction between the surface. High means there's a significant interaction between the two. And again, it can be because of the roughness of the surface. It can also have to do with intermolecular forces like you learned about in chemistry class, or you will learn about when you take chemistry class. Intermolecular forces are forces of attraction between particles, between atoms and molecules. Strong intermolecular forces can also increase this coefficient of friction. just the same as the roughness of the surface can. There are two separate values, one for static and one for kinetic, because again, they are two different things. And static is usually the higher number. This is a table of coefficient of frictions. So rubber on dry concrete. It's like the sole of a shoe on dry concrete has a static coefficient of friction of 1.1, has a kinetic of 1.0, the static being higher than the kinetic. Steel on steel, so something steel rubbing across something that is steel while it is dry. Static is 0.6, kinetic is 0.4. So again, much lower than rubber on concrete, so there's a lot less interaction there, but still the static is higher than the kinetic. Lubricants work by lowering those coefficients. So we have greasy steel on steel. The static drops from 0.6 to 0.12. It makes it slippery, it makes it easier to move, lowers the friction by reducing that coefficient of static friction. And the kinetic, 0.05, even lower still. You look down through the list, 1 is about as high as you go, 1 is a very high coefficient of friction. They go much lower, like 0.01, 0.003 down here at the very bottom. For the synovial joints in humans, one of the best lubricated things you can think of, one of the lowest friction things you can think of. Surfaces we consider slippery have low coefficient of frictions. So ice on ice, steel on ice. Ice skates, if you've ever gone ice skating, you know how hard it is because of the low coefficient of friction. That low coefficient of friction makes it hard for you to move and push off. Very low numbers, those are slippery things. Things that are grippy, again, a lot less sticky, will be a lot closer to 1, or more sticky, be a lot closer to 1 with their high coefficients of friction, like rubber on concrete or asphalt. From these observations, we conclude that coefficient of friction and friction are directly proportional. The more friction or more coefficient of friction you have, the higher that coefficient of friction is, the higher the force of friction is going to be. If you have twice the coefficient of friction, you would have twice the force of friction. If you had half the coefficient of friction, you'd have half the force of friction. Coefficient of friction and force of friction are directly proportional. Normal force and friction are also directly proportional as well. Normal force really tells you how hard the two surfaces are being pushed together. If you have a higher normal force, that means the two surfaces are being pushed together with much greater force, causing those hills and valleys in each surface to interact even more than they normally would. If you had a low coefficient, low normal force, you wouldn't have much force pushing the two surfaces together, therefore the ridges and valleys wouldn't interact nearly as much as what they would if it were higher. So here I have a 30 Newton normal force, a 30 Newton object. Here I have a 10 Newton object. This one would experience about, well, exactly, if the surfaces are the same, exactly 3 times the force of friction that this one would. And the reason it would experience 3 times more friction is because the normal force is 3 times greater. The two surfaces are being pushed together with 3 times as much force. Here's the equation showing those relationships to each other. This is the coefficient of friction. It has no unit, it's just a number. That's the normal force, that's the friction force. Two forces here mean both things are in newtons. The force of friction is equal to the coefficient of friction times the normal force. Again, both directly proportional. And one way you know that they're directly proportional is because they're both in the numerator of this equation. And you can think of that as being over 1. So both the coefficient of friction and the normal force are in the numerator of this equation, meaning that they are directly proportional to what's on the other side. So coefficient of friction is directly proportional to force of friction, and the normal force is directly proportional to the force of friction. Take a look at how it works. An 80 Newton wooden sled is being dragged across wet snow. What is the force of friction? 80 Newton wooden sled, that is the weight of the wooden sled. I've told you this a few times in a previous video. Whenever the newtons is attached to the name of something, 80 Newton wooden sled, that's its weight. And we know that the weight is going to be equal to the normal force. So if the weight's 80 newtons, the normal force is also 80 newtons. Coefficient of friction comes from this table over here. Wooden sled on wet snow. Wood on wet snow, there's two numbers, 0.14 and 0.10. I chose the 0.10, the kinetic number, because it is being dragged. That implies that it is in motion. We want to know what the force of friction is. That's the equation for calculating friction. It's the only one. It's the only one that friction actually comes up in. It's 0.1, the coefficient of friction, times the normal force of 80 newtons. 0.1 times 80 is 8 newtons of friction. There will be 8 newtons of kinetic friction that has to be overcome in order to keep the sled in motion. Take a look at another example. This one takes it another step. Here, all we're doing is figure out the force of friction. Here, we want to find the net force. And that implies that there's going to be more than one force acting on our object. An applied force of 100 newtons, it says force of, so that is a force being applied to the object, Fa, is used to slide a 5 Newton shoe. The newtons is attached to the name of something, so 5 Newton shoe means its weight is 5 newtons. If its weight is 5 newtons, its normal force is also 5 newtons. Coefficient of friction is going to be 1.0 because we're talking about a shoe across concrete. And it really doesn't matter if the other one here is dry. You have asphalt for the other one. It's going to be kinetic because it's being used to slide it, implying motion again. That's where the coefficient of friction comes from. We want to find net force. We're going to start with friction because that's what we've been given here to calculate the normal force and the coefficient of friction. 1 times 5 newtons of frictional force. Now to find the net force, we have to consider that there is an applied force of 100 newtons. So that means a force of 100 newtons is being applied. And opposing it, we have a 5 Newton force of friction. Calculate it like you would any other net force. I already drew it. They're in opposite directions, so we subtract them from each other. 100 newtons minus 5 newtons is 95 newtons. It'll be in the direction of the stronger force. Again, you could also assign values to these. Make this one positive because it's to the right. Make that one negative because it's to the left, and then add them together. Positive 100 plus negative 5. You're going to get the same answer. 95 newtons. It'll be positive because it's to the right. Let's take a look at this one. This kind of takes it into the real world scenario and asks it to analyze a situation and predict what's going to happen. A warehouse worker applies a 25 Newton force to a 150 Newton wooden crate as he attempts to slide it across a wooden floor. So it's wood on wood. Does the crate move? This is what I'm starting with. This is Fa. It's a 25 Newton force. That's the applied force. 1,500 Newton wooden crate. That's the weight of the Newton crate, of the wooden crate. It's equal to the normal force. The coefficient of friction for wood on wood, static this time because it's not moving yet. He attempts to slide it. Is 0.25 to 5.0. Now I start with the low number because if it's not going to slide for the low number, it's not going to slide for the high number. So I want to start with the low number, see if it's going to go. Find the force of friction first. Coefficient of friction times normal force. 0.25 times 150 is 37.5 newtons. Now, we're not asked for the net force. We're asked, does the crate move? The force of friction would be theoretically 37.5 newtons. The applied force is only 25 newtons. 25 Newton applied force, 37.5 Newton force of friction. That crate's not moving. That crate's not moving because the applied force is less than the force of friction acting on the object. It's kind of an analytical problem, trying to make a prediction about what's going to happen to this warehouse worker, and it's great. Let's do another one and see what we got working on here. This time what we're going to do is we're going to combine together an old equation with it. Remember, a lot of times in physics, to make the problems more challenging, we'll bring in old information. So we're going to bring some Newton's second law into this one. 8 Newton force, that is the applied force. 7 Newton aluminum block, that's the weight of the aluminum block. And again, weight is going to be equal to normal force. It's being slid across a sheet of steel. Aluminum on steel is being slid 0.47 for our coefficient of friction. We want to figure out acceleration. So we're going to have to figure out the forces first. Figure out what the force of friction is going to be first. This is the acceleration equation. And the acceleration equation tells us that the net force is equal to the mass of the object times its acceleration. Well, we don't have the mass of the object, and we don't have the net force, so there's not much we can do with that equation yet. We're going to have to start with the force of friction, figure out what it is, because that's really all we have enough information for. We have a normal force, we have a coefficient of friction, we can do this calculation. Coefficient of friction times normal force, 0.47 times 7 is 3.29. That's the force of friction. Now that we know the force of friction, and we have an applied force, we can figure out what the net force is that's acting on the object. I have an 8 Newton force going off to the right, that's positive 8 newtons. A 3 Newton, that's our friction, and I just rounded it to 3. Going off to the left, that's negative 3. 8 plus negative 3 is 5 newtons. We have a 5 Newton net force. So we have this number now finally. All of this math that we did right here, finding the force of friction, drawing that free body diagram, figuring out the net force, was just to get that one number that's missing right there. We still need the mass. And we don't have a mass over here, but we do have normal force. And normal force is equal to weight. So we can use the weight equation to find the mass of our object. 7 newtons, again, the normal force is equal to the weight, is equal to the mass times 9.81 meters per second squared, positive because all of these numbers are going to end up being positive when we're done. 7 divided by 9.81 is 0.7 kilograms. And again, newtons would be kilograms, meters per second squared. The meters per second squared cancel out, and all you're left with is kilograms. Now, finally, I have that number. I've got my net force, 5, that I can put in here. I've got my mass, 0.7 kilograms, I can put in there. It's time to solve. Multiplying by 0.7, so I got to divide by 0.7 to solve it on both sides. 5 divided by 0.7 is 7. Again, this is a kilogram meters per second squared. The kilograms will cancel the kilograms out, leaving you with meters per second squared. I had to use 2 old equations, a free body diagram, and my knowledge of net forces in order to get to the answer of that. Again, a very typical multi-step physics kind of problem.